Freeze-out radii extracted from 3 pion cumulants in PP, PPB, and PBPB collisions at the LHC. Abstract. In high-energy collisions, the spatio-temporal size of the particle production region can be measured using the Bose-Einstein correlations of identical bosons at low relative momentum. The source radii are typically extracted using 2 pion correlations and characterize the system at the last stage of interaction, called kinetic freeze-out. In low multiplicity collisions, unlike in high multiplicity collisions, 2 pion correlations are substantially altered by background correlations, e.g., mini-jets. Such correlations can be suppressed using 3 pion cumulant correlations. We present the first measurements of the size of the system at freeze-out extracted from 3 pion cumulant correlations in PP, PPB, and PBPB collisions at the LHC with Alice. At similar multiplicity, the invariant radii extracted in PPB collisions are found to be 5 to 15% larger than those in PP, while those in PBPB are 35 to 55% larger than those in PPB. Our measurements disfavor models which incorporate substantially stronger collective expansion in PPB as compared to PP collisions at similar multiplicity. One. Introduction. The role of initial and final state effects interpreting differences between PBPB and PP collisions is expected to be clarified with PPB collisions. However, the results obtained from PPB collisions at square root SNN equals 5.02 TeV have not been conclusive, since they can be explained assuming either a hydrodynamic phase during the evolution of the system or the formation of a colored glass condensate, CGC, in the initial state. As in PB-PB collisions, the presence of a hydrodynamic phase in the high multiplicity PPB collisions is expected to lead to a factor of 1.5 to 2 larger freeze-out radii than in PP collisions at similar multiplicity. In contrast, a CGC initial state model, IP-Glasma, without a hydrodynamic phase predicts similar freeze-out radii in PPB and PP collisions. A measurement of the freeze-out radii in the two systems will thus lead to additional experimental constraints on the interpretation of PPB data. The extraction of freeze-out radii can be achieved using identical boson correlations at low relative momentum, which are dominated by quantum statistics, QS, and final state Coulomb and strong interactions, FSIs. Both FSIs and QS correlations encode information about the femoscopic spacetime structure of the particle-emitting source at kinetic freeze-out. The calculation of FSI correlations allows for the isolation of QS correlations. Typically, 2 pion QS correlations are used to extract the characteristic radius of the source. However, higher-order QS correlations can be used as well. The novel features of higher-order QS correlations are extracted using cumulant for which all lower-order correlations are removed. The maximum of the 3 pion cumulant QS correlation is a factor of 2 larger than for 2 pion QS correlations. In addition to the increased signal, 3 pion cumulants also remove contributions from 2-particle background correlations unrelated to QS, e.g., from mini-jets. The combined effect of an increased signal and decreased background is advantageous in low multiplicity systems where a substantial background exists. In this letter, we present the first measurements of freeze-out radii extracted using 3 pion cumulant QS correlations. The invariant radii are extracted in intervals of multiplicity and triplet momentum in PP, square root S equals 7 TeV, PPB, square root SNN equals 5.02 TeV, and PBPB, square root SNN equals 2.76 TeV, which allows for a comparison of the various systems. The radii extracted from 3 pion cumulants are also compared to those from 2 pion correlations. The letter is organized into 5 remaining sections. Section 2 explains the experimental setup and event selection. Section 3 describes the identification of pions, as well as the measurement of event multiplicity. Section 4 explains the 3-pion cumulant analysis technique used to extract the source radii. Section 5 presents the measured source radii. Finally, Section 6 summarizes the results reported in the letter.